Assalamu alaikum. We are discussing the instrumentation, LCMS instrumentation, and today is the third lecture of the sequence. In the last lecture, we discussed the ionization modes and especially the electrospray ionization, its history, configuration, its functioning, developments and advancements, and also advantages and disadvantages of electrospray ionization. Today, we will discuss the remaining two types of atmospheric pressure ionization, that is atmospheric pressure chemical ionization and atmospheric pressure photoionization. As you know that the atmospheric pressure chemical ionization and atmospheric pressure photoionization, these techniques are generally preferred comparatively when the sample is less polar and smaller molecular weight, and as compared to the electrospray ionization. The atmospheric pressure chemical ionization is a type of chemical ionization, and although the interface design of atmospheric pressure chemical ionization is similar to electrospray ionization, but the ionization principle differs, and, and that make it more suitable for low and medium polarity compounds compared to non-polar molecules. In the atmospheric pressure chemical ionization, just like um, electrospray ionization, it has the capillaries for mobilizer gas and capillary for the sample that came from the LC column, HPLC column, a heater and the corona discharge. The self-starting corona discharge ion current in the microampere range is created as a result of the electric field between discharge needle and the curtain plates. So discharge needle and the curtain plates. The primary ions, for example, nitrogen, if the mobilizer gas is nitrogen, or oxygen, are created by a loss of electron that originate in the plasma in the immediate vicinity of the needle tip. The primary ions in turn generate intermediate ions that finally led to the formation of sample ions or analyte ions. Ions of chosen polarity drift under the influence of the electric field in the direction of the curtain plate and through the gas um, um, curtain into the mass analyzer. The whole ion formation process is Collision dominated because of the high pressure of API, APCI, except the immediate vicinity of the needle tips. Whereas the electric field strength is greater, the energy imparted to an ions by the electric field is small in comparison with its internal energy. Though the collision and the equilibrium distribution of certain ions is maintained, any excess energy that an ion may acquire in the ion molecule reaction process is thermalized through the process known as collision stabilization. Both ions and the reactant ion formation are governed by equilibrium condition at 670 torr operational pressures. The spray probe the spray probe of consists of uh, you can say the 100 micrometer internal diameter stainless steel tube surrounded by a flow of nebulizer gas. Here, the liquid sample flow is pumped through the sprayer, where it is nebulized into the quartz tube surrounded by the heaters. The inner wall of the quartz tube is maintained at a temperature of about 100, 200, 250, up to 400 degrees centigrade. When the liquid sample is pumped into the quartz tube, the sample and solvent are vaporized. I will show you in the next slide in detail. Uh, and the flow of auxiliary gas, you can say the gas 2, surrounds by the spray carries the vaporized sample through the quartz tube into the ionization region in the ion source. The liquid gas is introduced through a zero volume uh, LC fitted on the probe handled from uh, from where it flow the stainless steel tubing. The high velocity jet of nebulizer gas, yeah, the high velocity jet of nebulizer gas flow coaxially over the sprayer and to disperse the sample as a mist to fine mist of fine particles. A flow of auxiliary gas to sweep the sample mist through the quartz vaporized tube to the region where ion source pass the corona discharge needles, where the sample molecules are ionized. The mist or very fine droplets by the action of gas move here, here where the sample is ionized. The corona discharge in APCI source is formed by three major electric field and fluid flow elements: the corona discharge needle, a curtain plate, and the orifice lens here. The purpose of the corona discharge is to produce ionization of the trace species or sample gas, primary ions, where which are formed as a result of this discharge, are converted by Collision process to final ion molecule reaction procedure. The operators has the ability to set the corona discharge setting whatever they want at the application computer by adjusting the value of needle current. This is a little bit zoom diagram uh, to show the function at the mobilizer tip and in the ionization region. Basically, two type of steps occurred in this. The first one is the vaporization, and then the second one is the ionization. The vaporization starts immediate after the mobilization uh, by the action of heat, these heaters. The atomic atmospheric pressure chemical ionization vaporize the solvent and sample molecules by spraying the sample solution into the heater, and this heater has a temperature to remove the solvents by the action of gas as well. The solvent molecules are ionized by corona discharge needed to generate stable reaction ions. Protons are transferred These are the ionized uh, solvent molecules, and the protons are transferred from this stable reaction ions and the sample to the sample molecules and ion molecule reaction, and this lead to ionization. These ions molecule reactions are known to involve several patterns such as proton transfer reactions and electrophilic addition reaction. Nobilization and dissolution of atmospheric pressure chemical ionization mobilization is almost similar to that in uh, electrospray ionization. However, APCI mobilization occur in a hot, as I told, the temperatures is around 400. It can be set at 100, 200, 300, 400, 450, whichever as per the requirement of the sample. The heat rapidly due to this heat rapidly evaporate the spray droplets, result in gas phase, HPLC solvent and analyte molecules. Unlike electrospray ionization in APCI, a higher energy process, basically APCI involves a higher energy process and does not have the tendency to form multiple charged ions. This is an important point. Consequently, it is commonly used for analyzing high high fat soluble compounds or compounds that do not ionize in solution. In APCI, there is a charge transfer from the ionized solvent reagent ions to the analyte molecules in a way that is similar um, um, to chemical ionization in GCMS. These analyte ions then are transported uh, through the ion optics to the filter and the detector here. This is a more zoom diagram to show the what happened with the droplets that contain the solvent molecules as well as the analytes. And when it is separate or mobilized, and due to the action of the heater, uh, the solvent molecules evaporate. The solvents evaporate or become small and small, and the analyte molecules are free from the solvent. And the small, basically, you can say that the solvent, this molecule, this droplet is split into solvent molecules as well as the analyte molecules. And when the sample introduced through the APCI are sprayed into the heated probe with the aid of mobilization gas, and within this probe, the finely dispersed droplet of the sample and solvent undergo a rapid vaporization with minimal thermal decomposition. The gentle vaporization preserves the molecular identity of the sample basically. The gaseous sample and solvent molecules are swept from the probe, and the second gas, you can see here the auxiliary gas, into the ion source where the ionization of APCI, ionization by APCI is induced by the corona discharge needle. The sample molecules are ionized by collision with the reagent ions created by ionization of mobile phase solvent molecules. And then these ions, the analyte cations, uh, transfer to the mass analyzer. The vaporized solvent molecule ionized to produce the reagent ions. You can see the what happened basically. The solvent molecules ionized to from the cations, solvent cations, and and uh, and uh, and the ions to produce the reagent ions later on produce the reagent ions in the positive mode, and maybe in some case in the negative mode, S plus proton and S minus proton in negative mode. These reagent ions collide with the sample molecule. Here I mentioned the M as the analyte molecule, and this collide with the analyte molecules and convert it into the analyte molecular ion. You can see the stable sample ions. The sample molecules are ionized by the process of proton transfer in positive mode, or by either electron transfer or proton transfer in the negative mode as well. The energy for the atmospheric pressure chemical ionization process is Boolean dominated because of the high pressure of APCI source. Um, the atmospheric pressure chemical ionization is generally preferred for, as I told you, for the intermediate molecular weight of comparatively less and intermediate polarity or comparatively less polarity, like fatty acids, steroids, polycarbonated benzene, polyaromatic hydrocarbons, and the compounds that do not contain acidic or basic sites, and the sample containing heteroatoms, a sample that exhibit a poor electrospray response. They are we can use the APCI for that type of samples. And APCI also preferred if the solvent chemistry for the less sensitive to solution chemistry effect than ESI ions suppression, uh, and the best sensitivity of APCI at high flow rates as compared to the electrospray ionization, and also accommodate some non-polar solvents that not compatible, mostly non-polar electrospray ionizations mostly for the polar medium. So if the comparatively less polar or the non-polar solvent, we generally prefer the atmospheric pressure chemical ionization. But this technique is not preferred for thermally sensitive compounds because of the high temperature of the vaporization region. Another technique is the atmospheric pressure photoionization. This is also very important technique and mostly preferred for the very non-polar compounds. And this technique can be used in GCMS as well as in the LCMS. The photoionization has a long history uh, as the detection method for gas chromatography. It utilizes a discharge lamp instead of corona discharge that generate uh, vacuum ultraviolet photons. Atmospheric pressure photoionization basically ionize sample analyte by irradiation of short wavelength uh, uh, vacuum ultraviolet light. The interface design of APPI is very much similar. with the APCI, and only the difference with the swap of high voltage corona discharge needle to the vacuum ultraviolet lamp. Similarly, the nebulizer and the heater are used to create droplets and to vaporize the sample. The remaining process is almost same. Upon vacuum ultraviolet light radiation, the analyte absorb a photon and get electronically excited. If the analyte ionized energy is lower, this is important that if the analyte ionization energy is lower than the photon energy, the analyte ion that was ionized due to the photon may receive a proton from the hydrogen in the solvent to become a protonated cations. This ionization technique achieve good sensitivity ionization with low to moderate polarity compounds, polycyclic aromatics, for example. Um, again, the two steps, the vaporization step and the ionization step. The corona discharge is replaced with the vacuum ultraviolet lamp. The remaining process is same, the mobilizer gas, the sample capillary, and the droplets formed. And the heater facilitate the evaporation of the solvent. And it utilize a discharge lamp that generate vacuum ultraviolet photon. If the photons are absorbed by a species that has ionization energy below the energy of the photon, then single photon ionization may occur. You can say this is a direct ionization as well. And alternative reaction route may be takes if the carrier gas, such as suppose nitrogen, is used. The it strong absorbs the vacuum UV radiation and excited, and this excited gas when react with the analyte molecule and converted it into the cations. The photons formed by the two mechanisms generate a current which flow through a which flow to the collection electrode and form the signal in the chromatogram. The lamp is usually selected so that the energy of the photon is below. That is important. In the later slides, I showed you. I will show the table in which there will be the ionization energies of different solvents. The lamp is usually selected so that the energy of the photon is below the ionization energy of carrier gas and absorb the ionization energy of the analyte. The ionization energy of compound is dependent on the size and the structure of the compound. Large compounds and a compound that possess a high degree of conjugation typically have lower ionization energies than small and aliphatic molecules. Thus, typical analytes usually possess ionization energies in the range of 7 to 10 electron volt. In most cases, 7 to 10 electron volt. Whereas in GCMS, the common GC carrier gas have higher ionization energy values. Therefore, the analyte can be selectively ionized without interface from ionized carrier gas molecules. Often a krypton discharge lamp that emit 10 electron volt and 10.6 electron volt, a minor function photon is used. Uh, this is the same diagram, a zoom diagram of the droplets. What happened? Uh, the solvent and the analyte in the droplet, and the heater facilitate the evaporations and split this solvent analyte molecules, and then in the direct ionization, the analyte molecule absorb the photon and get ionized, and in the indirect or dopant added the first ionize nitrogen gas ionized, and then as a result the analyte molecules ionized and into the mass analyzer. The direct atmospheric pressure ionization is the photon directly ionize the analyte molecules, and the indirect solvent basically that molecule that is ionized uh, ionize the analyte molecules. And sometimes dopant added, and the dopant are easily ionizable species that absorb the radiation and ionize, and later this radiation this excited molecule ionize the analyte molecules in this case. And this table shows the ionization energies of some solvents commonly used as a mobile phase. And in conclusion, if we compare the uh, all three techniques, electrospray ionization, atmospheric pressure chemical ionization, and atmospheric pressure photoionization, the ionization process in electrospray ionization, the ions in solvent transition to gas phase by electrospray, and in APCI, the ionization occurs in gas phase by coronal discharge, and in API, in atmospheric pressure photoionization, the ionization occurs in gas phase by vacuum ultraviolet irradiation. And what type of ions formed in ESI? The single charged ions or maybe multiple charged ion forms, but in APCI, single charged ions, and APPI, the single charged ions are formed. And volatility of the analytes for ESI don't need to be a volatile, but for APCI requires some degree of volatilization, and for APPI also required some more degree of volatility. And the stability of analyte do not need to be thermally stable, can be thermally but for APCI and APPI, uh, the inlet must be thermally stable because heater is used, and if the temperature is very high, like 400 degrees centigrade, it can denature the analyte. Thank you very much.